In the last lecture, we have seen the applications of lasers in metrology, advantages of lasers, then various some of the examples of applications in metrology, that is a laser Doppler velocimeter, which can be used to find out the velocity of a moving component or length of particular object. Then we discuss about the laser diameter gauge, so we can measure the diameter of any opaque component, how it works, that we discussed. This is the commercial product, that is a laser diameter gauge. Then we discuss the laser viewer, so we can check the profile of any complex part, that can be done with the help of this laser viewer. Then after that we saw the laser scanning, so that was related with the lasers and its applications. After that we discussed the interferometry, so use of phenomenon of interference of the light for precise measurements. So how it is done, that we have discussed. Before that we saw the what will happen when the two waves are in phase, that is constructive interference. Two waves, what will happen when two waves are out of phase, so that is called as a out of phase by 180 degree, so that is called as a destructive interference. We've seen how the fringes are formed, that we discussed how the formation of fringes takes place. Then we saw this again principle of light wave interference. So the in an interference pattern we see the alternate layers of dark and bright bands. So the distance between two alternate dark bands is lambda by 2, and that represents each lambda by 2 distance indicates the elevation between the workpiece and optical flat as a h. Okay, so that we discussed. Then we saw the optical flat. What is the optical flat, how it is used, that we discussed. How to find out the difference between height of a master component. Now we have to see how to measure the difference between a gauge block and a component whose heights are not equal. As you can see, this is the gauge block set whose height is known to us, that is standard one, and its length is small l. Then this is the component whose actual height is to be measured. Then or we can say the difference between height of actual component and gauge block set, that can be measured. So our objective is now to find out the height difference between this component and this master gauge block set. Now the difference between position of, say, part A or component and gauge block set is capital L. So how this measurement is carried out? So as we can see, this component and gauge block, both the bottom side of both these, say, components is perfectly parallel and flat, and it is rung on this, say, base plate. This is a base plate. So by ringing, these two components are fixed on this base plate. An optical flat, this is the optical flat, it is resting on these two components in such a way that an air wedge is created between the optical flat and these two components, isn't it? So since, as we had discussed in the previous session, whenever there is air gap between an optical flat and a component, the fringes will form, fringe pattern will form. So here, as you can see, this is the optical flat and this is the gauge block set. So there is a air wedge between this gauge block set and the optical flat. This is the what we can say, this is the air wedge, amount of air wedge between optical flat and gauge block set. So due to this air gap, this fringe pattern is formed. Okay, this fringe pattern is formed because of the air gap. So accordingly, we can find out the height difference between this gauge block set and this optical flat, and that height difference is nothing but we can find out as n lambda by 2, where lambda is the wavelength of that monochromatic source of the light. So where and n is the number of adjacent fringes, black fringes. Okay, so by finding out value of n, we can find out this difference h, because in last session we saw that whenever there is a whenever there is a height difference of lambda by 2, the two dark fringes will be formed. So this is one dark fringe, another dark fringe. So this dark fringe is formed when this height difference is lambda by 2. Okay, so accordingly we can find out this height difference. So this height difference corresponds to length L. Now once we find out this height difference, that is a difference between top surface of the gauge block and the bottom surface of the optical flat, we can easily find out this difference h. So height of the air wedge is n lambda by 2. So difference in height is n lambda by 2 for this particular, for this air wedge, this one, the height of that air wedge is n lambda by 2. Lambda is the wavelength of the light, n is the number of adjacent black fringes. Now our true objective is to find out this height difference. If we find out this height difference, total height of this particular component can be easily find out, isn't it? So we can easily see that these two air wedges, so here also air wedge is formed, isn't it? This is the air wedge which is related to this particular component, and this is the air wedge which is related to gauge block set. And if we see that air wedges are nothing but the triangles, isn't it? So these two triangles which are formed due to the air wedge, both these triangles are similar triangles, isn't it? Both these triangles are similar triangles. So we can easily find out the number of fringes that can be formed because of air wedge between the optical flat and this particular component whose height is to be measured. Okay, so that can be predicted. So that is nothing but difference in height h is equal to n into lambda by 2 into capital L divided by small l. So what is capital L? This is the capital L, this is the small l. Because of the similar triangles, the fringes formed over small l are say n, then the fringes formed over the distance capital will be in the same proportion. Okay, that's why we can easily find out the number of fringes, and we can easily find out this height difference. So this h, small h, that is height difference between this gauge block set and actual component, is the n lambda by 2 into capital L divided by small l. Okay, so we have successfully found out the value of h. Now the next thing to be checked is whether the component is higher, or whether the we have to find out now whether this component is higher or gauge block set is higher. So that can be easily found out by one test. What we have to do, we have to just press this optical flat with the fingers. What do we have to do? We have to just press this optical flat by the fingers. So if you press that optical flat over the if you press that optical flat over the gauge block here, so if you press the gauge block over here, in that case what will happen, it will lift from, if you press here, this is in tilted position, so this side will go up. So as this side goes up, the air wedge will increase, isn't it? The air wedge will increase. So when component is higher, the air gap between optical flat and block increases, isn't it? So as you press here, this air gap between this optical flat and the gauge block set, that is going to increase, and as this increases, what will happen, the fringes will move closer. So this, whatever these fringes are there, these fringes are going to be all over here, isn't it? And as the gap increases, the fringes will get closer. Okay, so that will happen. So this happens only when the component is higher than the gauge block. Okay, and we can easily find out that the height of the component. Next condition, there is a possibility that this component is smaller than this gauge block set. Okay, so in that case, what you have to do, again you have to press the optical flat from on the optical flat from this gauge block set. So you press here with your finger. So in that case, what will happen, the air gap is going to reduce, isn't it? So this air gap will reduce, and as the air gap gets reduced, the fringes will move apart. So the distance between two fringes will increase. Okay, so in this way we can easily find out the height of any particular component, provided that you have a master gauge and the bottom surface and top surface of both the gauges, both the parts, that is gauge block set as well as the component, they are perfectly flat and parallel to the base. That is the condition. Okay, then next, interferometer can also be used to check the flatness. So in this case, what is done, the optical flat is placed on the metal surface to be tested. So what you have to do, we have seen the optical flat. So whatever surface you want to check, you just place the optical flat over the on the surface to be checked. So what will happen, the optical flat will not form a close contact, or you can say intimate contact. It will not form intimate contact with the metal surface, and if we view that through a monochromatic light, if we view this through a monochromatic light, a fringe pattern will be seen depending upon nature of the surface. So we will easily see the fringe pattern. So as we see the component through a monochromatic source of light, optical flat is on that particular component, that fringe pattern is seen, and that fringe pattern, so nature of that fringe pattern depends upon the nature of the surface. So some of the surfaces which are seen are shown in this particular sketch. As you can see, this is the flat surface. Okay, this is the flat surface which is not in good contact with the metal. This is a spherical surface, this is a sphere fringe pattern. This is a fringe pattern of the sphere. This is the, so perfectly you can see circles are there. Then conical surface, so it will look like this. This is a spheroidal surface. This is a convex or concave surface, as you can see. Then this is a surface having a ridge or valley in the center. Okay, so we can easily find out the type of the surface. You are actually going to perform an experiment based on this. So an experiment is there with the help of which you can see the various types of the surfaces. Then how the actual what is the principal operation of an interferometer? So we'll see that now. So here how the interferometer works, that is shown. So and as we discussed in previous sessions also, the purpose of interferometer is to measure something by using the phenomenon of interference of the light waves. Okay, so in a typical interferometer as shown here, the monochromatic source of the light is important, so that is shown over here. Single color of the light source is required. So that source, monochromatic light, is collimated by a collimating lens. So this is the collimating lens. So whatever is the source of the light, we will require the parallel rays of the light. So that's why a collimating lens is there. So it converts the source of the single source of the light into parallel rays of the light, or parallel waves, parallel beams of the light. So this light, after collimating, it falls on a mirror. So this is the mirror. So this mirror is partially silvered. It is a partially silvered. It is denoted by, say, letter C. So letter C corresponds to, referred as a mirror, which is a partially silvered surface. So whatever light falling on this mirror C, since this surface is a partially silvered, some of the light will pass below this surface, below this mirror C, and it will hit this workpiece and the table. Okay, this is the table, and on this table one workpiece is mounted. Okay, so half of the light will come in downward direction, and it will hit, or it will fall on the workpiece as well as on the table on which this workpiece is mounted, and from that it will get reflected. It will reflect back, and that we can see in the by our eyes. Okay, whereas half of the light which is falling on this partially silvered mirror C, that will be deflected in this direction, Okay, so that is reflected to mirror D. This is the mirror D. This is a mirror C. This is the mirror D. This mirror is fully silvered. Okay, fully silvered means nothing will go, nothing will pass. Okay, so nothing will refract. All this light whichever is falling on this mirror D, that will reflect back. Okay, so this all the light will reflect back from this surface. So that is a fully silvered surface is there. A flat piece of the glass equal in thickness to mirror C is introduced in the path of the light. So this is the flat piece of the glass equal in thickness is say introduced in the path of the light, just to equate the amount of glass plate in the path of the two light waves. Okay, so that is used. Now after so whatever light is reflected from this mirror D, that comes back to mirror C and passes through its partially silvered surface to the eye. So here there is a facility to see the reflected waves. So waves reflected from the workpiece and the table will be seen here, as well as the wave reflected rays reflected from this fully silvered mirror, that also can be seen here. Okay, now if the paths taken by these two parts of light are equal, so this is one path taken by the light waves, this is another path taken by the light waves. If the paths taken by these two parts of light, they are equal, then the workpiece and table surface, they appear as lighted one, or they appear as a bright to the eye. Okay, but if the paths differ by certain number of half the wavelengths, these surfaces will appear as a dark. So we have seen, if that is the basic principle of interference of light, that when two waves of same wavelength, they travel the different paths, and that if that path difference is odd multiple of lambda by 2, you are going to get the destructive interference, and the surface you will get the dark spot. Same is happening here. If the path difference between these waves and these waves, if that is odd multiple of lambda by 2, you are going to get the dark spot. If that path difference is even multiple of lambda by 2, you are going to get the white spot. So in this way, the alternate layers of the dark and light, dark and white bands will be seen. Now in order to use the interferometer for making the length measurements, so the objective is to measure the length of this object. Okay, in order to use the interferometer for making the length measurements, this table, whatever is this table, it is slightly tilted. It is slightly tilted so that small interference bands will appear on table and workpiece surfaces. Remember that this table is tilted, so you are going to get the two interference fringe pattern. One fringe pattern out of two sets of the two fringe patterns. One fringe pattern is due to the path difference between this mirror and surface of this mirror and this table surface, and another path difference is between this surface, the waves reflected from this surface, and top of the top of the surface of the workpiece. Okay, so by comparing the fringes obtained on the table and workpiece surfaces. So whatever fringe patterns obtained, so both fringe patterns obtained, those can be compared. Those can be compared, and we can easily find out the height. We can easily find out this height of the workpiece. Okay. So if the height of the workpiece changes, the fringes obtained due to the workpiece, they are displaced relative to the table fringes. Okay, so the fringes obtained due to the workpiece, they will displace with respect to the fringes obtained due to the table surface. Okay, so that can be used. This is the principle of operation of interferometer. Okay, so later whatever is seen we have shown here. Now how the NPL flatness interferometer work, principle of interference of the flatness interferometer. So as you can see, for this NPL flatness interferometer, or how these surfaces appear. So this is the constructional diagram of the NPL flatness interferometer. So there is a source of the light, condensing lens, there is a mirror, there is a green filter. So condensing light will take direct the source of the light on the mirror. The mirror will deflect the incident rays onto the green filter, then to the pinhole. This is a glass plate reflector, collimating lens. This is the optical flat. This is the base plate, and this is the surface to be tested. So here we want to check our objective. Our objective is to check the nature of this surface. Means whatever is this gauge is there, we want to check whether the top surface of the gauge, whether that top surface is perfectly flat or not with respect to the bottom of that gauge plate. So that is our objective. Okay, so the top surface of the gauge may be flat, perfectly flat. It may have taper. So this gauge will have length and say width, or it may be say length may be referred as a longer, so say edge, the width may be referred as a shorter edge. So there may be taper along the shorter edge, there may be taper along the there may be a taper along the longer edge, there may be taper along the shorter edge. So that we have to find out. It is possible that the corners of this gauge are worn out. It may happen like that. Okay, so let us discuss this now. So it is designed by the National Physical Laboratory, that is a NPL, mainly for checking the flatness. Okay, so interferometer is two types of interferometers are there. One can be used to check the flatness, and other can be used to check the length, the height of the gauge, or sometimes it is called as a length of the gauge. So this is basically used for the checking the flatness. Okay, so as you can see here, we'll see first the construction here. In this interferometer, mercury vapor light is used as a source of light. Now this light contains waves of different wavelengths, so we will require a single source of the light. So this light passes through the condensing lens and then goes to the mirror. So mirror will pass this light to the green filter. Now what this green filter does, the green filter removes all the colors except the monochromatic green. So here there are many colors are there, so out of that color only green, if green filter is used, it will filter only the green color. So only we want only one color, monochromatic light. So only green color is passed through this pinhole by this green filter. Rest of the colors are kept apart. Okay, so it is passed through this pinhole. So this pinhole gives the intense point source. So the objective is of this pinhole is to get the intensive source of the monochromatic light. So this monochromatic light will pass through this collimating lens, which will convert the rays of the light into parallel beams. Okay, so this parallel rays of the light, they will fall on the surface of this base plate as well as the surface to be tested. This is the surface to be tested. So these rays of the light will fall on both the surfaces. So in between this collimating lens and this gauge and base plate, there is an optical flat is introduced. Okay, so because of this optical flat, we are going to get the interference fringes we will get. So we will get two sets of the interference fringes. One set of fringe is due to the air gap between top surface of the gauge and optical flat. Another fringe pattern we will get because of the air gap between this optical flat and this surface of the base plate. Okay, and both these fringe patterns can be viewed in the eyepiece. So for that, a glass reflector is positioned. Okay, so we can see the fringe patterns through this eyepiece. Now various fringe patterns that are obtained with particular component and base plate are shown over here. So A, B, C, D, E. So these are the various types of the patterns that are observed. So we'll discuss this one by one. Say pattern A, pattern B, pattern C, pattern D, and pattern E. Okay, so pattern A is in this pattern. So one circle is shown, one rectangle is shown. This circle shown, this circle is nothing but it is a fringe pattern because of the air gap between the fringe pattern in the circle is because of the air gap between optical flat and the base plate. Okay, so there is air gap between optical flat and this base plate. So because of this air gap, you are getting this fringe pattern which is shown in the circle. Okay, so some horizontal lines are shown. Now it shows that now one rectangle is shown, and in that rectangle also some lines are shown, horizontal lines are shown. So these horizontal lines or this is the fringe pattern, or this rectangle shows the fringe pattern. That fringe pattern is because of the air gap between the optical flat and the gauge surface. Okay, so because of this air gap we get this fringe pattern. Okay, now so everywhere in all five sketches A, B, C, D, E, you will see one circle and some horizontal lines, and in rectangle you will see you may see some horizontal lines or curved lines or some curved lines like this, inclined lines also. So now we will compare the fringe pattern of which is observed inside the circle and fringe pattern observed inside this rectangle. Okay, so let us compare this one by one. So here if we compare the fringe pattern here and here, we see that the direction of the bands, these are the bands, horizontal lines are the bands. the direction of the horizon, these bands in circle as well as in rectangle, both are same, both the bands are in same direction. Okay, but the pitch is different. So what is the pitch? Pitch is the nothing but the distance between two adjacent fringes. So this is the pitch, this is the pitch, this distance from here to here, it is a pitch for the base plate, and this is the pitch from say here, from here to here, this is the pitch for the fringes because of the gauge surface. So if you compare this distance, the pitch is different. Here the pitch is more, here the pitch is less, but the direction is same. So it indicates that there is a taper along the larger end of the gauge. Okay, so as you can see, this gauge, okay, so the sorry, the larger edge of the gauge, top surface of the larger edge of this gauge is tapered. Okay, it is not perfectly flat. In second case, in case B, if we compare the fringes, these fringes and these fringes, the direction is same of both fringe patterns, as well as pitch is also same. Here this distance and this distance, pitch is also same. So this condition indicates that the surface of this gauge, top surface of this gauge is perfectly flat. This surface is perfectly flat. Okay, then there is a one more surface here. Again, if we compare this surface with this surface, okay, it indicates that here, as you can see, at the some corners, these are not, here there are straight lines, but here there are not straight lines, means here the corners of this gauge, the corners of this gauge, they are worn out. So that's why the pattern is like this. Okay, then fourth one, here as you can see, if you compare the fringe pattern here, so in this fringe pattern, as we can see, this fringe pattern is horizontal lines, all the lines are horizontal lines, isn't it? So in this case, as we can see, the fringe pattern inside the rectangle is not horizontal, but it is a curved line. So all the lines are curved, so it means it is either convex surface or concave surface. So how to find out whether it is a convex or concave surface? So a finger test is carried out, so that we are going to see when we perform the experiment. Okay, and there is one more surface. So as you can see, again in this case, if we compare the fringes of both, the fringe pattern obtained here, it is horizontal lines, where these lines are the inclined lines. So this, it indicates that the pitch is same. Here the pitch is same. Okay, the distance between this and this, pitch is same, but the direction is different. Okay, so if it is the case, it indicates that there is a taper along the shorter corner of the gauge. So in this gauge, there is a taper along the shorter edge. Okay, so just by looking at the various fringe patterns, we can easily find out the the nature of the surface. So we will stop here and we will continue afterwards.